Welcome back. This is section 2.4, linear inequalities. In A, we're asked to explain the difference between using parentheses and brackets when graphing the solution to an inequality. And then they want to know, did the same rules apply when writing solutions to inequalities in interval notation? So, when graphing on a line, we use closed dots and open dots. And basically this says that the value that is above, or that this is above, the solution is equal to that number. And this says the solution is not equal to that number. So for instance, if I had this as my graph, and I'm trying to graph a solution, so we're going to say we'll do a closed dot here, and we'll do, let's say, an open dot here. So what this says, if I was to translate this into interval notation, this says that from negative infinity to 0, and we're going to include 0. So I guess you could look at it like this. The bracket means include or equal to, and the parenthesis means exclude or doesn't equal or not equal to. And then we're going to use this symbol. It's a union, and what the union just means and. And this is what happens when you want to join. Like, see how there's a break in here between 0 and 1? So like if I said, what is the solution if x is 1/2? There's going to be no solution. What's the solution when x equals 0? It's going to be 0. What's the solution when x equals 1? Or let me rephrase that. These are values that you can plug into the equation. So could I plug 1/2 into the equation and get a value for y? No, because it would give me no solution. I could plug 0 in, but I couldn't plug 1 in because this open circle represents does not equal to or don't include. I could plug in values that are really, really close to 1 on the right side, the positive side, so like 1.99999 or 1.01. I could plug those values in. I just can't plug 1 in. Okay, so that's why I'm going to use this parenthesis, and we're going to go from 1, and we're going to go off to infinity. And that's what this arrow is telling me. It's telling me that just keep on going to infinity, and any number you want to plug in going positive after 1, we're good. You'll get a solution. So if I was reading this, I would say, okay, so from the solution set is from negative infinity to 0, including 0, union or and from 1, excluding 1 to infinity. So I hope that makes sense. And if it doesn't, that's fine, because we're going to do a whole bunch of stuff with inequalities in the videos coming up, and you'll start to see how we graph the solutions, and hopefully maybe it'll make more sense. This video is just a review, and hopefully I won't have to go too in depth. Do the same rules apply when writing solutions to inequalities in interval notation? Well, if this is graphing the solution and this is interval notation, can you see that the same rules do apply? I mean, I use different symbols, but the rules are the same. Okay, now we are asked to solve each of the following and graph their solutions. Alright, so here we go. This is going to be I. So we have negative 8k is less than or equal to 32. Well, they start right off the bat with something that is unique to inequalities, and that is if we divide by a negative or we multiply by a negative, then we have to flip this inequality right here. So I'm going to divide both sides of this equation, this inequality, sorry, by negative 8. And when I do, I'm going to say that k has to be greater than or equal to 32 divided by 8, or negative 8. A positive divided by a negative is a negative, and 32 divided by 8 is 4. So, okay, so this is my solution. Now, the second thing they want us to do is graph the solution. So, go ahead and do that here. So I say, okay, this is 0, and I always like to define where 0 is if I can. If I was trying to plot some big, huge number, or something like trying to say, okay, my values are only between 127 and 136, then of course I probably wouldn't show 0. But in this case, we're at negative 4, I'm going to show 0. And this is saying that the only values that allow this inequality to be true are values that are going to be greater than or equal to negative 4. So, and it does say equal to. And remember when in the last clip we said that closed dots mean equal to, and it's got to be greater than. So we go to the right, and there we go. This will be a graph of the solution to the inequalities. Now, what I like to do is, because it's very easy to mess this up, is I want to test a value. So do you see how 0 is to the right? And I'm saying here that 0 is a solution to this inequality. So what I do is I go up here and I plug in 0 into the equation. The original equation was negative 8k is less than or equal to 32. So negative 8 times 0, is that less than or equal to 32? And of course it is, because 0 is less than 32. So it checks out. So I'm going to go ahead and say that this is my solution. If you wanted to go one step further, you could ask yourself this. Pick a number on the other side. So let's say negative 5. Negative 8 times negative 5, is that less than or equal to the number 32? Positive times negative gives me a positive. 8 times 5 is 40. So is 40 less than or equal to 32? No. That means it wouldn't be a solution. And as you can see, I didn't mark it over here. All right. Let's do these in interval notation as well, so we can get some practice with that. Okay, so my solution is, and I'm just going to translate it right from this graph. So we're going to start with negative 4, and it's included in the solution set, and we're going to go to where? Infinity and beyond. So there we go. That's the solution set in interval notation, and this is the graph of the solution set for the inequality negative 8k less than or equal to 32. Alright, do double I. It says 5 minus 3r is less than or equal to negative 4. Alright, so we just go ahead and start solving this like we would anything else. So we have a negative 3r and I'm going to subtract 5, less than or equal to, and when I subtract 5, I get negative 9. And then I divide by negative 3, divide by negative 3. And when I do, I have to flip the inequality, and equals 9/3. And 3 times 3 is 9, so that's equal to 3. So R has to be greater than or equal to 3. Alright, so let's graph the solution set. Draw this line. Draw 0. I'll draw 3. And it does say it can be 3 because it says equal to, but it has to be greater than or equal to 3. And again, I want to go up here and plug in a value. So let's plug in 0. Is 5 less than negative 4? Absolutely not. So let's say 5. I plug in 5 here. I get 3 times 5 is negative 15. Negative 15 plus 5 is negative 10. Is negative 10 less than or equal to negative 4? Yep. So it checks out. So I'm comfortable with my solution, and now I am going to do it in interval notation. So for this, we are going to say that from 3, including 3, to infinity is the solution. Okay, triple I. We say, let's see, 2p minus the quantity 3 minus p is less than or equal to negative 7p. Man, this is a lot of p's. Minus 2, and a lot of constants. Okay, so I'm going to start simplifying here. So this is 2p minus 3. I'm just distributing this negative through here. Negative times negative is positive. 1 times p is p. It has to be less than or equal to negative 7p minus 2. And then I'm going to combine like terms. I have a positive p and a positive 2p, so we've got 3p minus 3 less than or equal to negative 7p minus 2. And add 3 to both sides. That cancels, and I get 3p equals negative 7p plus 1. And now I'm going to add 7p to this side. So I get 10p is equal to 1. Divide by 10. Divide by 10. P is equal to 1/10. Actually, and I'm sorry, I didn't it has to be less than or equal to, less than or equal to. P has to be less than or equal to 1/10. Alright, so since this is a fraction, what I want to do is I want to put some points in. So I got my 0, and 1/10 is 0.1. So I put what two values that it's in between, and then I try to, make it as close as I can, and we'll say that this is 1/10. And it does say equal to, so I'm going to use this closed dot. It has to be less than or equal to, and I'm going to draw that line there, and I would say that this is the graph of my solution. And we'll do it in interval notation. Interval notation would be from negative infinity, and like I said, I read it left to right, negative infinity to 1/10, including. And I just go back and check again. So 0 would be a solution. So I could use 0. So we go right up here to the original equation, and maybe even go down here to the simplified version of it. Let's use we'll choose this one here. So if 0 is a solution, then this goes to 0. And this goes to 0. And is 0 less than or equal to 1? I think so. And then what if we use 1? What if we plugged 1 in here? What do we get? 3 times 1 is 4. And negative 7 times 1 is negative 7. Plus 1 is negative 6. And is 4 less than or equal to negative 6? No. So that's why these aren't solutions over here. All right. Number 4. All right, this is a double, inequality double. So it's saying that negative 7. Okay, sorry, my wife interrupted me. So where was I? Okay, this is a double inequality. So less than 5. Alright, so basically what we're saying here is that everything in between these two inequality signs has to be true for y. So y has to, if I plug in a y, whatever this comes out to be has to be in between these two values. Greater than negative 7 and less than 5. Now, literally, this is like saying y minus 2 is less than 5 and y minus 2 is greater than negative 7. It's two different inequalities in one. And I think this is, it's really efficient if you're trying to pit something against two different values or you need something to be in between something. So, okay. And I'm just going to rewrite that down here. And we can go through it. So what you're going to do here is you're going to solve it just like you do these. So, for instance, this guy, I'm going to add 2, and over here I would add 2 and add 2. Well, what you're going to do here is you're going to add 2 to the inside, and that's going to cancel. And when you do that to the inside, you're going to do it to both sides. So you're going to get negative 5 is less than y is less than 5 plus 2 is 7. Okay, so our solution is, I mean, once we have y by itself in the middle, it would be no different than when this cancels, I get y is greater than negative 7 and y is less than 7. I'm sorry, that was confusing. I was like, what did I do? This is supposed to be negative 5, sorry. Okay, so we get the same answers. We got a negative 5 and a 7. And like I said, this is more efficient. Okay, so now we're going to graph our solution. So we draw a number line. And like I said, I'm going to define 0, define 7, and I'm going to define negative 5. And notice that I don't have anything that's equal in here. So we're going to have these open dots because they mean not equal to. So from negative 5, I'm going to have an open circle. And y has to be greater than negative 5. Okay? And y has to be less than 7. But it can't be 7. So I use an open circle again. And the value has to be less than negative 7. And then what you can do is you can look at this and just draw a little line there. And you can see that these values satisfy both equations in here. So what I'm going to do here is write this in interval notation, and I'm going to take all that into account. So my solution set is this. The values for both of them are true between -5, and I was getting ready to do that, wasn't I? I know you caught me. Okay, not including all the way to 7. Not including. So this would be the solution set to this. So now I'm going to test a value. I'm going to test, like, say 10, 0, and -10. And I'm just going to plug them in here. Okay, so 10. Is 10 greater than -5? Yeah. But is it less than 7? No. So 10 can't be a solution. -10. Plug -10 in here. Is -10 greater than -5? No. But it is less than 7. So it can't be a solution. 0. Is 0 greater than -5? Yes. And it's less than 7. So there we go. And we can see that it satisfies both equations here when 0. When 10 would be over here. Notice that it only satisfied one of the equations. And -10, notice that it only satisfied one of the equations. Okay, so now we get into something a little more fancy. So -1 is less than 5y plus 2 divided by 3. And that has to be less than or equal to 4. Alright, so I'm going to multiply both sides by 3. -1 times 3 is -3. And 3 times 4 is 12. Now I'm going to subtract 2 from everything. And I get -5 is less than y plus 2, which is less than or equal to 10. Oh, I'm sorry. See, like I said, I'm going to make mistakes. And hopefully I'll catch myself. I should have went like that. Okay, now we are going to divide by 5. Those are going to cancel. And we get -1 less than or equal to y less than or equal to 10 divided by 5 is 2. Okay, so there we go. My solution set is this. Y has to be, there's no equal sign for -1, so I'm just going to draw a closed dot. And y has to be greater than -1. And notice how I take my time with inequalities. I try not to speed through them. I try to take more steps when I do inequalities than I do solving an equation, because there's more chance for error, and there's a logic that goes along with the inequalities that you really have to be careful with. And you're really going to notice it with, and I'm sure you've done them, but the absolute value problems. Okay. And actually, I'm going to catch myself here. I made an error right there, because this has to be greater than, it can't be equal to. So it would be an open circle. And then at 2, we're going to have a closed circle because it can be equal to. And y has to be less than or equal to this value. So we're going to go to the left. And then -1. It's so hard to draw a straight line with this thing. Okay, so now I'm going to set it to interval notation, my solution here. So notice that it can't be -1 because it doesn't solve. It doesn't satisfy both of the equations. It only satisfies one of them. And then when we get to 2, it satisfies both equations. did it again. So I say one thing and I do another. Awesome. Okay, so -1 not including, 2, and we're going to include 2. I think that's why I make a lot of silly errors on my tests, and I lose valuable points for making those silly errors. All right, and now we look at number 6. It says that 8 is less than or equal to 1 minus 3r is less than 16. So we're going to add 1 or subtract 1 both sides. And we're going to get 15 3r. 8 minus 1 is 7. And now we're going to have to divide by -3, and when we do, remember, we're going to have to flip. So this is going to be -7/3. And I flip. Got an r left there. I flip this. And I get a -5. 15 divided by 3 is 5. Negative or positive divided by negative is negative. And I'm going to graph the solution. And we say, okay, 0. Call this -7/3 and -5. Alright, so it says it has to be, the solutions have to be less than or equal to -7/3. So they have to be less than or equal to -7/3, but they have to be greater than -5. Alright, so what I'm thinking here is, notice that there's no double line anywhere. And I'm just going to go back just to make sure. So my r value has to be less than or equal to 7 divided by 3 is going to be, oh, well, there's where I messed up. Sorry about that. I don't know what the heck I was thinking. I'm just going to redo this part right here. And this was my 0, this was my -5, and this is my 7 divided by -3, and that's going to be 2 1/3 negative. So that's going to be about, what, right here? Okay, so it has to be greater than, or less than, or equal to this value, -2/3, and it has to be greater than or equal to 5. Alright. And then draw those lines to show where those values are double lines, here and here. And then I'm going to put in interval notation. So notice that it can't be -5. I like this pink. And it can be -7/3. Alright, so there's the solution set. And I would like to point something out here, because I think it's important. Like I said, I do these on the fly, and I'm going to make mistakes. And the question is there enough logic to catch your mistakes, or my mistakes, per se? And I think it's important, like problem-solving strategies, where you get to see, like, well, what happens when these guys, that are doing these videos, or, math teachers in general, I always pay attention to what they do when they do make a mistake, and how they go about figuring out how they made a mistake, because I think that's a really important problem-solving strategy. So look at this. Look at what I did here. I said this was 0. I said that this was negative 7/3, which it wasn't, and this was negative 5, and I went like this. Now here's the question. Is there, talking about like domain and range. Domain are the inputs of x, and the range is how high it goes when you put in these x's. So can you think of any number that I couldn't have put into this right here? I guess they're inequalities, so I guess there could there be like no solution? Let me think about that for a second. Okay, I think I have a better idea of what I was trying to say. Okay, so these are the x values here, right? These are the inputs that I'm going to put into the function. And basically what this graph is saying is that here I'm saying that I can't put in any numbers over here. So I can't plug in negative 6 because it satisfies this one, but it doesn't satisfy the other one. Over here what it's saying is that if I plugged in, say, 3, it satisfies this one, but it doesn't satisfy this one. But notice that somewhere there is a value of x, or r in this case, that would satisfy this equation. There's at least one, and of course there's more because there's a range. But look down here. What this says is that if I plugged in a number over here, say 3, it's going to satisfy this one, but it's not going to satisfy the other one. But right here, this says that if I plugged in this value, I'm going to get no solution. Now, no solution is when the denominator is 0. Or when the x's would cancel out. Like if you had negative x plus 2 is equal to x plus 7. Negative x plus 7, something like this. So when I add x and I add x, the x's go away. And when I subtract 2 and I subtract 2, I get 5 is equal to 0 x's, or 0. And there's no solution there. So there's no value that would make this true. But in this case, notice that I had negative 3r. And I didn't have any other r's in the equation. So there was no way for that to happen. And notice that there's no fraction in the equation. So there's no way for me to get a 0 in the denominator. So the thing couldn't break. So since that was the scenario, this could not be the solution. And I'm glad that I caught myself when I did, because I would hate to give out misinformation. And I'm sure that from time to time I will. But anyway, so hopefully that will, bring rise to, why things happened the way they did, and how, what my line of logic was to catching my little mistake, or rather, big mistake, actually. All right, moving on. So we'll go with this one. It says the absolute value of p is less than 7. Alright, so that means whatever number I put in here has to be less than 7. So we're going to go to the definition. And the definition basically says this. And the way that I think about it is that if you look at the absolute value function, it looks something like this, right? That's what it looks like. And remember, when you're looking at absolute value, just the absolute value, so this is the absolute value of x, we'll say, that all of the answers are positive. Pick a number, pick any number. Pick 745. If you plugged it in there, you get positive. Pick 745 in the negative direction. Pick a number, you're going to get a positive answer. And this is the graph of this, right? So the two cases are going to be if p is greater than 0, so from here over 0, we get the positive case. And if p is less than 0, we're going to get the negative case. So pick a number, pick 2. If I input 2 for p, 2 is greater than 0, so the answer is just 2. If I pick negative 2, and I plug negative 2 in for p, because it's this case, right? I'm going to get a positive 2. And I know, like, I had some trouble with this, and I know a lot of students have trouble with, well, what's the two cases? Why the two cases? So I just thought I'm trying to put another spin on this thing, to maybe, make you understand it more. All right, so anyway, just remember, there's two cases with absolute value, always. Okay, so what we're going to do is solve this inequality. And we're going to write it over here as two cases. So p is less than 7, and negative p is less than 7. So here we go. So p has to be less than 7. So this is 0, this is 7, and it has to be less than 7. Not including. And here we're going to divide by -1. Divide by -1. And when we do that, we're going to have to flip. So we get p has to be greater than -7. So we go -7. And we punch in a open circle. And we go this way to infinity. Okay, so now what's going to happen is there are double lines between -7 and 7. We agree? Hope so. So there's 0. And what I'm going to do here is I'm going to test the values to make sure. So is the absolute value of 0 less than 7? Yes. So that works out. Let's go over here. 8. Absolute value of 8. Is that less than 7? Nope. Doesn't work out. And the absolute value of -8. Does that work out? Absolute value of -8 is 8. Is that less than 7? No. So values over here don't work out. So our graph to the solution looks accurate. So I'm going to put it in interval notation. So from -7 excluding to 7 excluding are going to be the answers to this absolute value inequality. All right. Let's clear this, and we'll go with the last one in this section. Okay, 7. It's going to be absolute value of x minus 1/2 is less than 2. So again, we're going to have two cases. We're going to have x minus 1/2 is greater than 2. And we're going to have negative, or the opposite of x minus 1/2, less than 2. Alright. So now we can divide by -1. When we do, we get x minus 1/2. Flip the inequality. -2. Remember, I divided this thing by -1. That canceled with that. I divided this by -1. Or I could have distributed and added and then divided by the -x. However you want to do it, it's fine. Alright, so then we add 1/2. And we say that x has to be greater than. Alright, so -2 is -4/2. Plus 1/2. It's going to be -3 halves. And then on the other side here, we have plus 1/2 plus 1/2. That's a mixed number. And that's going to be 5/2. Alright, so now we're going to graph the solution here. Okay, so 3/2 is 1.5. So I'm going to mark 1 and I'm going to mark 2. This is, and it's negative. -1, -2. There we go. And x has to be greater than and not equal to. So go like that. And then over here, x has to be less than 5 divided by 2 is, I'll put us right here. And again, it's x has to be less than this value, but it can't be equal to. That was terrible. There we go. That looks a little better. Okay, so you notice that our values are in between these two values. And you're going to find a lot of times that this is going to be the case with these absolute value functions. I do want to go over here and test a value. So I'm going to test 0. So if this goes to 0, minus 1/2 is going to be -1/2, and the absolute value of -1/2 is 1/2, and that is less than 2. -2 is going to be -2 minus this guy, so it's -5 is going to be bigger, so that's going to be wrong. And then of course this guy's going to be bigger than 2. So our solution set is going to be from, I forgot to mark these, didn't I? Okay, so from 3/2, from the negative, excluding, to 5/2, excluding. And we checked it because we said 0 was right here, so that looks good. Alright, so just real quick, just remember, anytime you have an absolute value function, you're going to have two cases. You're going to have the positive case and you're going to have the negative case. And when you're through with your inequality, be sure, even if they don't tell you to, draw this line graph. So that way you can see where these values are common to both of the inequalities. If you have a single inequality, and I guess we should have done, did we do one of those? I think we did. We did the absolute value of p. It was less than or equal to some value or whatever. So we had that one. And then we had the flip. So yeah, just remember that there's two cases, and always, 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 whenever you're doing the inequalities, especially when you're doing these two cases, make sure that if it's like the absolute value of 2x plus 5 is less than 0, something like that, make sure that when you do your two cases and you have this positive case, and I'm going to change this to a 2 so that way it makes a little more sense, is less than 2. When you do your negative case, do not do this. 2x plus 5 is less than negative 2. Don't do that. Make sure that you actually write it out, because you're going to get the negative case is the opposite of whatever is inside here, and that has to be less than negative 2. And then when you distribute, and then you add that to the other side, so what's that going to be? Positive 3. And then you divide by this negative 2, you get x has to be greater than, because this sign flips, greater than negative 3 halves. Now, just to reiterate this is negative quantity 2x plus 5, and that has to be less than negative 2. You can divide by that negative 1 like I did in our example, but when you do, make sure that you flip this. And we're going to get 2x plus 5 is greater than, has to be greater than 2. And then I subtract 5, and this is where this negative 3, this is how this negative 3 gets over here. Negative sign gets over here this way. It's kind of cool how all this just works out. So this is x has to be greater than negative 3 halves, and x has to be greater than negative 3 halves. Notice that they're the same, which, I mean, intuitively they should be, but if we did it this way, we would have gotten the wrong answer. And I think that the knowledge is what they're looking for when they're testing us, so it's important to show that, hey, you know, I know this stuff, and I know when I can do it and when I can't do it. They always say, you got to know the rules before you can break them. And that concludes section 2.4. Stay tuned for 2.5.